Okay, clear enough. Yes.
Okay. All right. We. All right. So good afternoon, Mr. Reddy and Kadevita. So today we're back again into the thermal regulation in PCR chamber project, but today in the second milestone. So just for reminding that we are dealing with the thermocycler, which is we want to regulate the heat temperature of the sample between the denaturation process, the annealing, and the extension process. And what we have done in the previous milestone is that we have already designed the circuit connection, the rough design. We also have determined the materials and equipments that are needed, and we made a rough design for the thermocycler, including the casing itself. And from that, what we have done in the previous milestone, our target for this second milestone is to obtain the required material and equipments and to construct the thermocycler circuit in detail and perform a program for the Arduino. Okay, Jess?
Circuit diagram and yeah, circuit diagram. Okay, so and the main elements for our device here is are the heater, cooler, and also another cooler. Okay, for the heater, on the previous milestone, we planned to use a nichrome wire heater, but since there were some errors and problems, so we decided to use a 12-volt 40-watt cartridge heater. And for the cooler, just as the previous, the planned as previous milestone, we use the Peltier kit that includes heat sinks. And for the other cooler, we use a 12-volt cooling fan. And for the other cooler, so this is the circuit diagram that we've built, the ensembled circuit here. So you can see, yeah, the you can see the Peltier cooler, the source, the breadboard, and yeah, so on. Oh, okay, so deeply about the power source and the connection. Well, we plugged in to the LN from power line here to the 12-volt source, and for the DC output, we plugged in from the negative, we plugged in from the positive, we plugged into the relay, and for the from the to the negative, and the negative is connected parallel with the other main components, main elements.
Next is the four channel 5 volt relay connection. The first one is to connect the elements, the positive terminals of the elements, to the COM of the relay. And for the heater, yeah, we also connect all the cooler and heater to the COM of the relay in parallel. So, and DC, for the DC source, we connect in parallel to the normally open of the relay. And we also need an isolation for the relay. We connect a 5-volt DC adapter to JD VCC for the positive and the negative to the ground. And every input of this channel is connected to the digital pin of the Arduino. For example, the first channel is to digital pin 8, 2 to 9, and 3 to 10. We also connect the VCC into the breadboard. And this is for the Arduino connection. We managed to use an NTC 3950 since it has two legs. One leg is connected as a power and one leg as an input to the breadboard. And we make a pull-down resistor of 10K ohm here, and we connect into the analog input A0. And for the power, we connect all this power from relay and the NTC to the Arduino, and we connect the Arduino to the computer. And this is basically the thermocycling system. It is basically similar to the previous milestone because we have like found a lot of research that also use this kind of design where we put directly the heater under on top of the cooling elements. And for the heater, we used a cartridge heater. It is sandwiched between two conductors of aluminum plate. And for the cooler, it is attached to the small heatsink and the large heatsink for the hot side. And also a 12-volt cooling fan in the hot side of the Peltier module. We also connect the NTC 3950 to the container.
Okay, calibrating the sensor. Okay, since Arduino cannot read temperature, so we need to calibrate the sensor. So Arduino can only read resistance, right? So we used Steinhardt equation here to calculate and to measure the temperature. So, but first we need to find the three coefficients here in the equation, which you can see there, A, B, and C, there. So we're going to use the following matrix equation here to find the three coefficients. Okay, so firstly, to find these three coefficients, we're going to use three different temperatures here. So for our calculation, we used 60, 70, and 80. So after choosing these temperatures, we're going to see the resistance for each temperature here. As you can see, 60 is 2.472, 70 is 1.735, and 80 is 1.243. So after knowing the resistance for each temperature, we're going to insert it to the matrix equation, and also insert the temperature to the equation also. And then after inserting, we're going to inverse the matrix and then multiply it. And then, as you can see there, the result of our calculation is written below.
All right. So actually, we haven't really got the results of the thermal cycling itself, but however, we have already tested the on and off the process of turning on and turning off the elements. But however, we also have already made the program for the final thermocycling process. First of all, we define the pins and integers and variables. We define which digital input or analog input that the elements are connected to. And this is the temperature for the each process of the PCR. We define the temperature and also the cycles, and we include the Steinhardt equations also. So before it begins the loop, the void setup, we begin by determining which output and input in the Arduino. So the main components are such as the heater and the cooler. It is connected as an output, and for the thermistor, it is connected as an input. All right. And also here, we want to heat the heater first, hit the container first for 10 seconds. So that is preheated. When we want to begin the PCR process, it is already in the hot environment. So this is the third one is for the void loop. Basically, we just want to like reach a certain range of temperature. Like for example, for the denaturation process, we want to increase the temperature uh, by um, by turning on the heater. And notice that this is low instead of high because we connect the elements to the normally open of the relay. So that means when low current, the elements turn on. So for the annealing and extension process, and after the loop is complete, we increase the cycle. If it reaches 30, the process is complete, and we also manage to determine the temperature. This is using the Steinhardt equation, and for the reaching specific temperature, it is basically when we want to reach the denaturation temperature. If the temperature is less than the ideal temperature, the heater is going to turn on, and the cooler is going to turn off. And so for the if the temperature is higher than the ideal temperature. So the challenges that we were facing with in this second milestone is basically the heat transfer. We still don't know the transfer of the heat from the heater to the conductor and finally to the sample. And secondly, the system capability, well, the time taken of the capability of the system for rapid heating and cooling process. And thirdly, the safety, because we're dealing with high current circuit. And second, we don't want the sample to be contaminated. And so the solutions for these challenges are for the heat transfer, we measure the temperature of the conductors and also the containers. And secondly, for the system capability, we regulate the heat first at for approximately moderate temperature, like 50 centigrade, and then we increase the temperature gradually until it reaches the denaturation temperature. And for the safety, because we're dealing with high current circuit, we use fuse, so it breaks when there are way much current that flows in the circuit. And we also want to build a casing for the thermocycler for the next milestone. If it is um, if we have if we
Time.
easy to find the materials.
Yeah, okay, so expectation for the next milestone is that we expect to have very accurate and good result for our from our device, and we also expect to have solution. What do you call it? We expect to have manage our to manage to face our challenges for the next milestone, so we can present to you guys the very good result. Yeah.
So that was it for this presentation. Thank you very much.
Thank you, Group 6, yeah, Jesse and Hanif. So I would like to request Group 5, Osama and Martin, to ask question. Osama and Martin, please ask question. Please turn on their videos as well. There's Osama. Osama right there. Yeah, drop questions for Jesse and Hanif.
So I want to ask in the structure, in the design of the. Can you go to the slide to the design? Okay. For the chamber, why do you put the cooler on the bottom of the heater? Will
It's
it cool the
actually, oh
chamber?
yeah, okay. So we have also like received an advice from the previous milestone that we don't connect the heating element and the cooling elements. However, we've also like read some of the stuff about the design, and if we build a large container and um, the Peltier cooler is not directly cool the heating elements, it will be, I think it will be not really efficient for the rapid cooling process. So that this is basically just a rough sketch. We also like want to make preparations here, but as long as the peltier does not really contact to the aluminum, the heater, sorry, it is separated by the heat sinks and the aluminum here. I think it is safe.
But how do you rapid cooling the chamber if the Peltier cooler is not touching the chamber itself?
Because it's the cool actually goes here. We've already like tried to like operate this Peltier cooler, and on the top of it we receive like cold temperature, especially when the temperature the Peltier cooler is has been turned on for a long time. So I
Okay,
think it is, yeah.
thank you.
Thank you.
Osama, any question?
Mm, yes, I have a question. So I still don't get the idea why the conductor is needed, um, and why you don't put it under the plate directly.
The heater.
Yeah.
What? Sorry.
Okay.
Well,
Sorry. What was it again?
yeah.
The question?
Why the conductor here is needed? Why you don't put it directly under the heater?
Oh, why we cover it with the aluminum plate? Yeah.
Yes.
Oh yeah, because so it won't directly touch the Peltier cooler, and also so that the heat transfer from the heater will spread like to the aluminum plate, and will also spread to the to the chamber, to the what do you call it? The apa? The what's the name again? The place where
So
the substance is put.
yeah,
The
the container.
yeah, the container. Yeah, sorry.
Yeah, so
Yeah,
basically we
so
want to increase the surface area of the heater.
yeah,
So yeah, so the cartridge heater itself, it is like it is like tabung, so it's
Tube,
small and
a tube.
yeah, a tube. Okay, and we've also read some of the design that using a cartridge heater requires an U squared aluminum, and then on top of it, we also cover it up with the aluminum plate. But it's kind of hard to find aluminum that is has like certain um, length of thickness. Yep.
Okay, thank you.
Okay, Kak Devita, maybe one question. Kak Devita, are you hearing me? Hello? Hello, Kak Devita, we cannot hear you.
she's still muted, sir.
Yeah, I cannot unmute. I can ask to unmute, but she has to unmute herself. Kak Devita, we cannot hear you yet. Can you please unmute yourself? Hello? Yeah, no question, no reply. So anyway, yeah, and if in this, I have a similar opinion with Martin, yeah. So it just doesn't make sense
Sorry,
for
sir.
me. It just doesn't make sense that you have your cooler and chamber, the cooler and heater both underneath the chamber.
Uh, well, actually, like we've already seen the designs also.
Okay, can you show
Like
us the chamber again?
oh wait,
The
hold
setup.
on. Yes, here.
Is it, can you amplify or zoom into the chamber only? Nothing.
Okay, here.
Okay. So what is what there? What is so this is the chamber, right?
Yes,
Then
chamber.
Yeah,
what else? This one is what?
The heater.
heater, sir.
Heater. Okay.
Yeah,
This one is
is
Heat
that one is
sink.
the heatsink, and the
say
underneath is the peltier inside the
yeah.
heatsink.
So what is
Not
between
that
them?
one.
Just
Not that one,
separated
sir.
by
It's
Underneath the heatsink, like directly underneath the heatsink, it is the peltier.
underneath the heatsink is the peltier. Where is your
Uh,
thermistor?
Wait,
oh,
here, sir.
there, sir.
This is the peltier here.
Where is your thermistor?
Thermistor here.
Thermistor here. Okay.
Yeah.
Have you tried this?
For the whole PCR process, not yet. We just
Yeah. Look.
randomly.
Yeah, this is the one that you need to control. The one
Yes.
whose temperature you need to control. So
Mm.
if you put the peltier under the heater, you are basically cooling down the heater, not the chamber. So
Mm,
it would be, yeah, I don't know if you could put this too many, sorry, not, yeah, if you can put them maybe, I don't know, upside down or something like that, or at the side, for example, the peltier, so that it cool directly the liquid in the chamber.
Uh, sir, if is it possible to put the, is it okay to put the heater in beside, sir, rather than the Peltier cooler?
Yeah, it is possible. Why not? As long
Because yeah,
because what now is you are cooling down the heatsink and the peltier. You are not cooling down directly the chamber. Yeah, eventually maybe you turn off the heater, then eventually the chamber also will cool down. But I think the effect of cooling will be faster. Your response time of your cycler will be faster if you put the peltier touching the chamber.
directly, yes, sir.
Yeah.
mm.
From physics, yeah, from physics. This is not from electrical engineering. It's from electrical circuit. analysis. But from physics point of view, you can ask Pak Fatoni if you don't trust me. Don't believe me. If you ask Pak Fatoni, not yet. Ask him, try to ask him. Yeah.
Right.
Even this one can be modeled from using the finite element modeling, but unfortunately, yeah, maybe you will get that modeling in next semester. I'm not sure. I will ask Pak Fatoni to teach you how to model physical system like this, yeah, to model the heat transfer. So if you have very hot material between the chamber and the cooler, your cooler will require lots of power to cool down the chamber. Okay. So
Okay, sir.
again, I re-emphasize my comments already in the first semester that you should not put them stacking like this. You put them directly to the chamber. The heater attached to the chamber, the peltier also attached to the chamber. The chamber is the system that you want, whose temperature you want to control.
Okay, sir. We thought that the pellet cooler was in the power from the pellet cooler was enough, sir. Like to from the peltier to the chamber if we make it like this.
It will power consume. It will require more power, and number two, it is requiring longer time to cool it down. That's why I asked you if you tried or not. Yeah, apparently you haven't tried, but from physics point of view, it will take longer time.
Oh, okay.
Okay,
Okay.
Okay, sir.
don't repeat the same thing because we have put give you suggestion from the first master. Also, your friends also agree. So yeah, if you don't agree, you try, and then you try both configuration. Which one will be more efficient
Yeah.
in terms of time, also in terms of power consumption.
Okay, sir.
If you can prove to us it is work same and even better,
Okay.
it's good of you.
Yeah.
Okay,
we
sir.
will comply. Okay, thank you, Group 6, Hanif and Jesse. So we will now move on to the second presentation by Group 4, Nikki and Michelle.
Thank you, sir.
Thank you, Nikki and Michelle. Okay. Yeah, you may.
Oh, wait, sir.
Okay.
Not yet.
Yeah. Okay, you may start as you are ready. When you are ready.
Hello?
Okay.
Okay. Good afternoon, Sir Dedi and Kak Devta. Today we're going to present our project, and this is the milestone 2. So this is the devices that we use: voltage regulator, voltage to current converter, LCD display, heater, and PWM pin as an active temperature sensor. So for the voltage regulator, we use transistor C1815, capacitor 100 microfarad, one piece of 1K ohm resistor, and jumper wires. For the transistor, this one is to control the voltage, and for the capacitor, it's to filter the noise because it can harm the Arduino. And for the 1K ohm resistor. This is to reduce current because transistor C1815 works in low current. And this is the Arduino Uno, and also the battery 1.5 volts, 2 pieces plus the holder. And the Arduino parent pin is for control the amount of signal produced. This is what we working on. So this is the behind it there's transistor. The transistor, the emitter one connected to 1K ohm resistor, and then also to jumper wire to Arduino pin 10. And for the collector, it connected to capacitor, the anode one or the short leg, resistor 1K ohm, and the LED, the short leg one. And for the base, it is connected to the capacitor, the cathode one or long leg, and the battery.
For the voltage to current converter, we are going to use either LM741 or LM358 because I cannot find LM358 here. Next, we also are going to use 3 pieces of 10 ohm 2-watt resistor, and we are going to parallel it to form 3.33 ohm. Next. Here, we can see that LM741 and LM358 LM358 can change the function of LM741 if only the left side that is being used. So they can replace each other. LM358 can replace 741. Next. We also use jumper wires and 2 pieces of 9-volt battery for the VCC and VEE. Next. This is the principle of our current converter. We are going to use floating load voltage to current converter. From this graph, we use an op-amp, so the voltage in the inverting input and the non-inverting input is the same. So we can calculate the I passing through the load by using this equation, VIN over R. R is the R2. Next.
This is for the LCD display. We need 220 ohm Arduino digital pin and jumper wires. Also the LCD 16 times 2 and 1K potentiometer. This is the LCD we made.
Next, for the temperature active sensing, we are going to use nichrome wire 80 with AWG24. We also use Arduino digital pin and jumper wires. Next. Based from this reference, and we are using 24 AWG, we gather this data from different temperature, and then we make a graph. Next. This is the graph that we make, and based from this graph, we find the equation current is equal to this equation, and then we could see that the current and the temperature form a linear relation. Next. So for the reference temperature, we make it 35 degrees Celsius. So based on the equation that we have derived previously, we calculate the current needed, which is 4 to 7.8 milliampere. Because the current exceed the maximum current from the Arduino, we have to use external source. We use the resistance 3.33 ohm, and then we have a voltage source of 3 volt. Because of that, the maximum current that can be supplied by the circuit by the converter is 0.90009 with the maximum power of 2.70027 watt. Because the power is still below the minimum power of the resistor, because the maximum power have to be divided by 3 because it is parallel, so the resistor is still safe to be used. Next. This is the equation that we have derived. So we to find the delta I, we are going to use the I reference and V reference. We also use Vx. Vx is the voltage in the current time. So for the active temperature sensing, we are going to measure the on-time voltage by using the Arduino. We are going to measure the voltage passing through the heater. In the lower left part, it is not T reference, it is T. There's a typo. Next. This is the working progress that we have made. The left part, the LCD, and then the battery, the positive part, which is the black wire, is connected to the non-inverting input of the amplifier, while the red one is connected to the capacitor leg. This inverting input, which is the red wire, and then the non-inverting input, it is the yellow wire. And then the red wire, which is connected to the ground, it is the NC part. It is the part of the amplifier that cannot be interfered. So we connect it to the ground. The blue wire is the output. The output is connected to the LCD. To the LED. LED is the representation of the Nicom wire. And then the Nicom wire will be connected to the green wire to the resistor, while the yellow wire, which is the most concave wire, it is also connected in parallel with the green wire. And then the resistor is formed in parallel form, and then the resistor will be connected to the other leg of the capacitor. Next.
This is our coding plan. The first one is to equip the OPM with power supply. The second one is making a circuit consisting of a voltage to current converter, voltage source, and nichrome wire. The third one is to apply various temperatures to the nichrome wire and record the voltage across the circuit to form the voltage versus temperature graph and forming the equation. And the last one is to apply various current to the nichrome wire and record the temperature of the nichrome wire to form the current versus temperature equation. And that's all for today. Thank you for listening and have a good
Michelle
day.
and Nikki. I would like to request group 2, Catherine and Elisa, to ask question for Nikki and Michelle. Catherine and Elisa, please turn on your videos.
I see the potentiometer in LCD. What is the function of potentiometer?
Oh, it is to adjust the voltage
Catherine,
to the
can
LCD.
you turn on your video, Catherine? Where is Catherine? Yeah.
Okay, so this potentiometer has functions to adjust the voltage to the LCD so that the characters can be seen.
Okay, thank you.
Any other questions from group 2, Catherine and Elisa?
I have a question. So I'm still confused about what is the exact relationship of the temperature, the resistance, and the voltage, because I'm still not quite, I still don't quite understand it yet.
Yeah, good question. Okay, Michelle, can you? Yeah, your presentation was rather bit difficult, yeah, to follow actually. Can you explain again?
Uh, so because we are using current source, the one that is changing is voltage. We use nichrome wire. Nichrome wire is a type of heater with a PTC characteristic. It means that the temperature higher, the resistance is higher. Due to the resistance is higher and the current is fixed, so the voltage will increase when the temperature increase. Because of that, both the temperature, the voltage, and the resistance are all directly proportional. Does that answer your question?
Yes, thank you.
Okay.
Kak Devita, maybe one or two questions.
Okay, ready? Yes. Yesterday you asked me how to troubleshoot your Arduino, right? So is it already solved? Your Arduino, Nikki?
We try to fix the LCD by rotating the screw at the back of the LCD, because in Google it is said that when firstly to be used, it has to be fixed first if the LCD is not working.
Yes, but what about the Arduino? I think your Arduino, is it still working or
Yes, it is still
short?
working. It is
Also, yeah. Okay then.
still working.
Yeah. Okay. Okay, Pak Dede. I think that's all.
Yeah, I will just follow up the questions from Elisa. Yeah, Nikki. So resistance change, when temperature increase, resistance increase, then voltage increases. So how does your controller algorithm work to be able to? You need to control again the heater, right? When temperature, if you touch the heater, temperature increases, for example. Resistance increase also. With the constant current, voltage will increase. Yeah. So what to do? You need to. There is a feedback mechanism, right? But
Yeah,
done by the Arduino. What kind of feedback mechanism?
we are going to reduce or add the current by using the PWM regulator. So when the voltage increases, we lower down the current. Because the current is being lowered down, the voltage will also be lowered down.
Okay.
And then because of that, the temperature
Yeah. So actually,
will start to
active temperature
get
sensing.
lower.
Yeah. I'm sorry, yeah, because your sound putus-putus. So
Oh, okay.
in active temperature sensing, actually the temperature is indicated by the control signal that you send to the heater, rather than the measured delta V from the voltage meter. You understand? So it is the active control signal, the control signal that you send from the Arduino to compensate the temperature increase, that is actually indicate the temperature of the whatever that touch the heater. You understand? And that point is with what Elisa was asking, and which is not yet clear in your presentation.
So if we try to measure our temperature, we have to measure it using the change in current. We cannot use.
That's why the control signal.
The change in voltage, even though
Yeah,
we know how
it
many
is
colors.
related. They are related, but actually it is the control signal that will indicate the temperature. Yeah, similar like when you have you know old balance. Yeah, sorry, I'm
Yes.
you know an
The
old
one with 2 arms. Yeah.
yeah, the one with 2 arms.
Yeah.
So this is the example I give. Yeah, then you put, for example, a sack of rice, right? Then it will drop like this. Then you have this weight, yeah, that you can slide to the left or to the right, right? You never
Yes.
you never see
Yes.
this.
I have one in my house.
Okay, this is usually large balance, not small balance. This is large balance, and the amount that you adjust the delta L here. There is a scale, of course, here. There's a scale here. The amount that you adjust here, basically you are compensating the moment. Next semester you will have statics. I will teach static for you. So that then it will balance again. So after like this, it will balance again. So this is maybe you slide to, this is the original position. You slide to here. So this delta L indicate the delta M you put in the left side of the balance. So the principle is similar like that. Only now you are speaking about voltage and current and heat. Okay.
Okay, sir.
Yeah. So please, yeah, you are getting towards that. Only, I don't know. Maybe I do not understand your presentation clearly, or maybe that part is just missing from your presentation numbers. Anyway, thank you, Group 4. So looking forward for the final session. Then we move to the next group. Group 3, Dev and Dimas. And I think because Dimas is ill, only Dev will present.
Okay. Let me share my screen first.
Yeah.
Okay. So good afternoon, everyone. I'm from Group 3, which consists of me and Dimas, but unfortunately Dimas cannot join. So yeah, we'll just start. I just start with the theoretical overview. This fast. So PCR stands for polymerase and chain reaction, where polymerase is enzyme that makes polymer of other molecules, which in this case is the DNA. Chain reaction is a type of reaction where it progresses in an exponential way. And yeah, this is overview of the PCR thermocycler process. There's the three big process here. First, the denaturation, which happen in 95 degrees Celsius, and then annealing at 55 to 65 degree, and extension at 72 degrees Celsius. So here's overview for relay connections. There are two types of relay connection: activating relay and deactivating relay. So just like its name, when the lights turn on, when relay will also turn when the relay is turned on, the load will also turn on. And also, while the deactivating one, when the relay is turned on, then the load will also turn off. In this case, we use this deactivating relay connection. And next is project progress. So here's what we use for the materials. And here's the circuit schematic that we end up using. But here we use 100k ohms for the fixed resistor. And we postpone the use of LCD. And next is the programming part. So our program's anatomy actually have three parts, which is first the value controller, and then the temperature reading, and also the thermocycler. First, the value customizer. So here we put interface where we can just change the value, so it's easier for us. Here's for the temperature reading, and here's for the input and output pin. And here we can actually customize what desired cycle we want, and also the thermocycle process time, how long will we want each process to undergo. So here's just the overview of how temperature reading, of how the temperature reading goes. So here's the how we find the resistance value. ADC is an octo digital converter, and then this is the Steinhart equation, and also we will need to find the beta equation first by using two different temperature and also resistance that we can obtain from the table of the products. And also we want to show the temperature in Celsius, so we will need to convert again from Kelvin to Celsius. And here's the temperature reading code. So I'll not explain everything, I'll just explain the blocks of the code. So first, here's the, we make a variable to store the value later on. And then we want to calculate average resistance. Why? Because since the reading might be noisy, we want it to be more accurate. So we take 15 samples each second and average the value. And then here is the thermistor resistance calculation. And also we convert it to Celsius. So yeah, here's is the algorithm flowchart. Basically, we'll go again and again. This is just for example, if the cycle is equal to 10, so it will go again and again. And if it's finished, then it will go back to room temperature. And here's the thermocycler code. So for the big loop, we use while loop, and also for the denaturation, we use for loop and while loop to control the heater. Then we basically the opposite. We want to set it to high to be able to turn on the heater. And then to sustain, we use the if statement, conditional statement, and control it using the while loop. And we basically do the same thing for the other process. And for the end touch, we use also a cycle counter so that the loop can go on and on. And also we can get the notification whether if the cycle finished or not. Next is the hardware. So yeah, this is just the connection diagram. And yeah, this is the preview of our hardware. So we actually use a can and we insert the heater at the bottom of the can so that it can spread evenly. And we put the peltier at the up of the can so that the heat can go away from the upper side. And yeah, just for safety, we use insulator at the bottom. So here's the connectivity preview. It's a bit rummy. And yeah, problems that we encountered. First, there's actually we've tried to reach the maximum temperature for the heater several times, but then what we will get is 63 to 64 degrees Celsius at maximum, which is not actually reaching the denaturation process. So we cannot actually try the code that I've explained before. And then second thing is the container material. This is really confusing because the one that we think ideal, which is the can, is actually we actually try to use the continuity test in the multimeter to test whether it's conducting or not. And since the can is not conducting at all, and also we try to touch the can, it's not that hot, so it's not really effective. We also try to use usual households products, And yes, it is conducting, but it's too thick for the heater to heat it up. And also last one is the LCD library error. The LCD that we have is the one that use the I2C backpack. We actually already tried to adjust the potentiometer, but yeah, it doesn't really show up anything. Uh, and we cannot actually use the usual liquid crystal library. So we actually need to use the contributed libraries, and we've tried 3 different libraries and none working. So that's really unfortunate. And yes, that is all. Thank you for listening. And any question?
Thank you, Dave. So I would like to request group one, Alicia, Darren, Gracia, to ask questions to Dave. Please turn on your video, the asking group.
I'll ask first. Why did you use a 100k ohm resistor? Why didn't you use a lower value?
Yes, because provided in the from the Arduino kit, there's no 10k ohm. So if we make series of 1k ohm resistor, it's going to be really crowd. Uh, but actually, it doesn't really affect much because in the calculation, the resistance value is just for the fixed value. So we can just change this to 100k, then we will actually get the resistance value. So yeah, it doesn't really affect.
Okay, thank you.
Okay, next from me. Dave, is there any difference in your algorithm from the previous milestone and in this milestone?
Yes. For the overall algorithm, there's actually no changes, but for the controlling parameter, in the first milestone, we use delay, so we use time to control the temperature. But now we use the temperature reading itself to control the temperature, so it's more responsive, and we don't really need a lot of trial and error. Yeah.
Okay, thank you.
Okay. Darren, any question?
Before you mentioned that you have a problem with your temperature limit, right? So how do you plan on solving the temperature limit?
Yeah, we actually maybe by adding another heater. So we use more than one heater, but I'm not really sure if it's going to work. I haven't tried it at all. And also maybe we want to solve for the container material, which is not thick and can conduct heat.
Okay, thank you.
Okay, Kak Devita, maybe one question.
Maybe I just want to give suggestion. Yeah, for the flowchart, I think there is a missing arrow. It's
Oh yeah.
the flowchart. The flowchart, can you show me? Yeah. I can show the. Yeah, I think. Then there's missing, ada yang salah kayaknya sama flowchartnya ya. You have to give extension apa ya maksudnya menyambung flowchart. Nanti cari tahu lagi caranya how to menyambung flowchart. This is not the right way.
How to extend flowchart? Yeah, using the connection.
Using
Usually we use circle, something like that. If
yeah,
please find the device.
small circle.
Small circle. Yeah, try to look around in the Google. You can Google how to write a flowchart.
Okay.
Yeah, and thank you, Badaki. And then for my next suggestion is if you try to do the data taking because you are playing with high temperature, yeah, please make it safe. Make sure that you are safe. Maybe you can use some glass fuse. You can search it on internet, yeah.
Yeah, because the
So
current
with
may
the
be
current.
very high. The current is
Yeah.
high, so you need to use fuse for safety. Yeah, for safety reason.
Yeah.
Okay, Dev.
Okay, I think that's all, Pak Deddy.
Yeah. Okay, thank you. I have question.
Oh, okay.
But well done actually. Yeah. So you have also some preliminary results. So about the temperature, I think very good. Yeah, very good. Only can you show the setup again? You mentioned because you cannot reach 95 degree at the denaturation
Yes.
temperature. So if you can you show me which one is what? This one is what?
Oh, this is the Peltier.
You have
with,
Peltier as well.
Yeah, Peltier and the fan.
Peltier and fan. Okay, it's the cooler. And heater is where?
Heater is this one, the cartridge wire. We insert it to the bottom.
Oh, to the bottom. So heater is in this part.
Yes.
Okay. Okay. So what is inside here?
The can.
The can is tall enough to reach this part. Yeah.
Yes.
Okay. Peltier, which one is Peltier? Which one is fan? This is fan. I can see it.
This part, the plane here is the Peltier, and also there's the heatsink a bit here.
Okay. Sing. Yeah. Perhaps the Peltier needs to be attached directly. Touch, yeah, very close contact, in contact with the heat sinks is above the Peltier. I think, maybe. Yeah, okay, the Peltier is attached to the can, and the heat sink above it. The fan doesn't matter. The fan can be anywhere. But the Peltier, because it needs to cool down directly the chamber, I assume it might be better to have it attached directly. So, okay, yeah, that's my suggestion, Dave. Then, if you want to heat it up properly, where is your thermistor? Sorry, I forgot. Where is your thermistor?
Directly inserted to the can.
Where? I cannot see the connection.
This one.
This black one. Then attached to where?
It is waterproof, so you can.
Okay. Oh, okay. In the middle.
Yes, deep.
Yeah. Okay. So based on now, what is the highest voltage you apply or highest current? Heater.
For the heater, we use the adapter 12 volt and also for ampere current.
Ampere. Okay. Yeah. But cannot reach 45 degrees.
Cannot reach
95.
more than 60.
More than 63. You use nichrome heater.
Nichrome heater.
What heater do you use?
Cartridge heater wire.
Cartridge heater wire. Why don't you use nichrome like the rest, like the other guys?
Yeah, sir.
Cartridge heater wire, how high can it reach?
I asked the seller. It says that it can reach higher than 90 degree, but seems that it doesn't reach that much.
Cartridge, yeah. You mean for printer cartridge?
Yeah.
The heater for printer cartridge, thermal ink.
Yes.
Now the problem is, in thermal inkjet, yeah, the chamber is very small for the ink. It's why within that small chamber, it can heat up until very high temperature to make the ink push as droplet. Yeah. But now your chamber is huge. That can is how many milliliter?
I didn't measure.
Yeah, but yeah, still it is 15, right? At least 15 milliliter. That small can. You get what I mean? If you have, you understand? You don't understand? If you have like this, you have big one. This is your heater. For example, this is your heater. The same voltage, the same current, same voltage, the same current. Okay, power equals to PI. okay, of our V square R or I square R. Okay. Now, with the same power is being put into the chamber, into both chamber. Which one you think can reach higher temperature?
This one.
Yeah, the small one. This is not in electrical circuit analysis. This is in physics.
Yes.
If as Pak Fatoni taught you about thermal analysis.
Yes, yes.
Yes. So this is by law. This is it has like Q equal to M mass, right? C times delta T, right?
Yes.
Okay, Q here equals to the power. So power times time. So equal to voltage, current, time. So the delta T equals to how much? Power times time divided by mass times the specific heat. So if the mass is small, yeah, the smaller the mass, the higher the delta T you can reach. You get it? You understand?
Yes, yes.
If your mass is large, the delta T will be small. So this is for all groups, yeah, doing the PCR. So if your chamber is like this huge, it will require a lot of power to heat it up, and it will require also a lot of time to heat it up until 95 degree. You know the chamber in real PCR,
No, sir.
very small, very small. This very small. Maybe only how many? 10 milliliter. No, less than 10 milliliter. Less than maybe 100 microliter or something. Or 0.5 milliliter. Okay. So you have to make it smaller. Maybe I don't know this size. Even smaller. The smaller the better. So then you can heat it up quickly, more quickly, and to high temperature with small power, with small required power. Clear?
Clear, sir.
Okay, so I hope you can revise your design, especially the chamber design. This one goes to group 6 also, Jesse and Hane. And okay, so I think that will be all for this first session. Let's have a break. Thank you, Des. Yeah.
Thank you, sir. Thank you.